Hello, welcome, and thank you for watching. Today we're going to derive the equations of kinematics, which come from Papa Isaac Newton, one of the most renowned physicists ever. And we're going to start with a very simple equation that you probably and hopefully have seen before, which is force is a mass times acceleration, and we're going to get all the way to an equation which can tell us definitively where a particle will be at any given time based on initial conditions. So it's very powerful to know and very useful. And so this is where it came from. Using calculus is what we're going to use. So force is a mass times acceleration. You probably heard that before, but what you may not have heard is it is also simply the way that a momentum changes with time. The derivative of momentum with respect to time. That is mass times acceleration, because if you also remember, momentum is just mv, mass times a velocity, so that's dp dt. If you consider the mass constant, you can arrive at this result. And then if you remember that the way velocity changes with respect to time is acceleration, you just have acceleration for that derivative. So it's ma, that is the same thing as dp dt. So that's very useful to know. And we can begin with a very simple example. So all we're going to do is an example straight out of this book, Statistical Mechanics. I'm not going to do any statistical mechanics, I'm just going to do simple physics, but it's one of the first examples in the book because it's really cool and really powerful to understand. So we have a one-dimensional system. All you're going to do is launch an object up in the air, subject to gravity, and determine exactly where it is at any time based on the force of gravity, the acceleration due to gravity. So using the latter two of Newton's laws, first, force is a mass times an acceleration, which is a mass times the way that velocity changes with respect to time. And the third law, which is that for every action, there's an equal and opposite reaction. So for the force of some object, ma, there's an equal and opposite force, which in this case is gravity, mg, with the opposite sign with the minus. So considering an example of a bowling ball being shot up into the air, right? We have it on the floor, it's shot up with some initial velocity, goes up into the air. We want to determine at any time, where is it? Or at any time, how fast is it going? You may think that's really hard to do only with an initial velocity. Like, how can you determine that easily? But you can because of calculus and Newton's laws. So that's what we're going to do. So we start from here, and we remember a couple things. First, acceleration is the way that velocity changes with respect to time. It's the way that velocity changes with respect to time. So if you remember derivatives, let's say v is our function. It's a function of time, so the velocity, let's say it's moving the same speed, and then it's faster and faster and faster, then it moves the same speed, etc. This is one plot of an example of some velocity over time. The way that it changes with respect to time is the derivative, right? So at this instantaneous moment, it's changing like that. It's going up, it's increasing. So dv dt is the acceleration. It's the way that velocity changes with respect to time. Okay. Likewise, velocity is the way that position changes with respect to time. So velocity is how position changes with respect to time. If you look now at where something is as a function of time, say it starts here and then it goes far away, and then it's in the same place, and then it goes farther away. During these moments, it's staying in the same place. If it's staying in the same place, the speed is 0. The velocity is 0 because the way that position changes with respect to time is that it isn't changing. So here you can say that the velocity is 0 because it's dx dt, right? So it's pretty intuitive once you get a little bit of practice and you see it more and more. So this is acceleration, this is velocity. Let's use this acceleration here, okay? So mass times the way that velocity changes with respect to time is equal to a minus mass times the acceleration due to gravity. right there. So now to simplify things, let's say our bowling ball has a constant mass, so it's not going to lose its part of its mass or gain it. And in doing that, we can divide by the mass on both sides. We just get rid of it. We don't worry about the mass for these equations. We assume constant mass. Okay, so now we're here. If we integrate this with respect to time, we can get a useful result. So let's take the integral of dv dt with respect to time from initial time 0 to some whatever time t. That's going to be equal to the integral from 0 to t minus g with respect to t. Right? So here we have dz dt, which would cancel. And so our integral would then become simply dv at t minus, not dv, sorry, v at t minus v at 0. Right? So v at whatever time t minus v initially, which we can call our initial velocity, v at time 0. That's just v naught. Okay. That's from the fundamental theorem of calculus, right? We're just subtracting the value at here and the value at here. So on this side, integrating from 0 to t of just some constant g, you end up with minus g times t. You just get a t. You also get minus g times 0, but g times 0 is 0, so that's not a term to worry about, so the term here is irrelevant. That being the case, because g is a constant, so it's not g of 0, it's g times 0. Here it's dv, not just v as a constant. So it's v at 0, not v times 0. So there's a difference there. So this is 0, we don't need to worry about it. Now we're here. Let's just do a little easy algebra. Moving v naught to the right. Get that. So what we now have is one of the equations of kinematics. This equation can tell you, for a given time, and for an acceleration due to gravity that you know, like on the Earth, it's roughly 9.81 meters per second squared. Everywhere you are, roughly equal to that. Given those two parameters, you can determine exactly what the speed is at any time. So at 5 seconds, how fast is it going? At 4 seconds, how fast is it going? 3 seconds, how fast is it going? You can know that. That's one of the equations of kinematics. Now there's one that's even more interesting probably, which tells you not the speed at any time, but the position at any time. So now we're going to get the position with respect to time. So that's kind of more interesting, because then you can know not just how fast it's going at 3 seconds, but actually where it is at 3 seconds. Again, only with the information that you know how fast it's going at the start. That's all you need to know. And acceleration due to gravity in this case. So remember that v is dx with respect to t, the way position changes with respect to time. Right? So dx of t with respect to time is v naught minus gt. Simple as that. I'm leaving this v naught because it's already a constant that we already know, so we don't want to express that in terms of some way that position changes with time. We just want to leave it. So we're here now. We're almost to the most interesting equation of kinematics. If you integrate both sides, just like we did before, with respect to t, you get a very interesting result. So if we take this from 0 to t, this side from 0 to t, with respect to t, with respect to t. So all I did is integrate both sides with respect to t, 0 to t. You get this. The dt's here cancel, leaving you with dx as a function of t. So from 0 to t, you get x at time t minus x at time 0. So it's x of 0 or x naught, the original position. That's going to be equal to some constant integrated from 0 to t dt, which would be that constant times t is all. And then this g times t integrated from 0 to t dt, right? So that would be 1/2 g t squared, right? It's just like x integrated from 0 to x dx, right? It's 1/2 x squared, easy, with constant thrown in. So now we're here, and I'm just going to move this part over to arrive here. So this result, super cool and super useful. This equation is, to me, the coolest equation in kinematics because it can tell you the position of a particle. It can tell you the position of a particle at any time as a function of time. If you know the initial position, which we can say in our case is simply 0 for the bowling ball, right there. Here it's 0, it goes up maybe 1 inch, 2 inch, 3 inch, 1 meter, 2 meter, 3 meter, whatever. The initial velocity that you threw it up by, the time that you're interested in, and the acceleration due to gravity. That's all you have to know. So that is a derivation of Newton's equations of kinematics using Newton's laws. It's pretty straightforward if you just do a little bit of calculus. We have derived two equations of kinematics starting from two of Newton's laws, the second and third laws. First, any force is a mass times the acceleration of an object, and that there's an equal and opposite reaction for every action. So if there's a force that the bowling ball or the bullet or the planet exhibits, then there's an equal and opposite force also applied, right? In this case, the equal and opposite force is gravity because we're launching the bowling ball up into the air. So our bowling ball is here. Let's say its initial position is 0. That's where it starts. We call it 0. We launch it up in the air at 50 meters per second. So it's straight up in the air. Let's ask ourselves, how fast will it be moving at 4 seconds? So how fast will it be moving at time 4 seconds? Well, all we need is the initial velocity, 50 meters per second, minus the acceleration due to gravity times the time. So I'm doing a rough estimate of the acceleration due to gravity here. The real number, which you probably heard before, is 9.81 meters per second squared. That is not a fundamental physical constant. That's an approximate true value for anywhere on the surface of the Earth, because it is dependent on the distance between the body of interest and the center of the Earth. But this is what works for Earth near the surface. It's roughly this value almost exactly in almost every place. So I'm going to just use 10 for that, just to simplify things. So let's look at this. At 4 seconds, the velocity is 50 minus 40, which is 10 meters per second. So what's interesting about this? At 4 seconds, when you've launched the ball up into the air, 1, 2, 3, 4, it slows down. It started at 50 meters per second, but now it's only 10 meters per second. Consider if we waited for 7 seconds to look at the velocity. So after you launch it, how fast is it moving at 7 seconds? Well, that would be 50 meters per second minus acceleration due to gravity times 7 seconds. So here we have 50 minus 7 minus 20 meters per second. So that means, it may seem counterintuitive, but it's true. It's a negative velocity with respect to the velocity you started with. So this makes sense. If you launch the bowling ball up into the air and gravity is being applied, after a certain point of time, it will not be moving up and have a positive velocity anymore. It will have a negative velocity and move down. So we have a negative velocity at 7 seconds. So somewhere between 4 seconds and 7 seconds, the bowling ball is going to stop going up and come down. And that's determined. We have the equations for that, and that's why it's really interesting and really useful. So let's think to ourselves, okay, what about the position at these times? What about the position? So the position is basically just as straightforward. At 4 seconds, look at this. The initial position is 0 meters. We add initial velocity times the time, 4 seconds, and we subtract 1/2 times acceleration due to gravity and the time squared. So this would be our position after 4 seconds. That's just 200 minus 16 times 10 is 160. 1/2 of that is 80. So this is 80. 200 700 minus 80. That would be 120 meters. So at 4 seconds, the bowling ball is now 120 meters up in the air. Let's think about where it is at 7 seconds. So you give it even more time after the launch. So in this case, you would have initial position 0, initial velocity 50, times the time, minus 1/2 acceleration due to gravity at 7 seconds. Okay, 50 times 7 is 350. And this is 7 squared is 49, 100, or 10 times that is 490. 1/2 of 490 is 245. So here we get 350 minus 245, which is 105 meters. So again, we find something pretty interesting. It may seem counterintuitive, right? At 4 seconds, you've launched it up in the air, it's 120 feet up in the air. At 7 seconds, you'd think, well, it's been longer, so it must be further up, right? But no, gravity is applied. Gravity is applied, and it's subtracting more than we were subtracting before. So you end up with a position in the sky 150 meters up instead of 120. So by the time, again, you get to 7 seconds, it's going down. So it's useful to understand. Those are the equations of kinematics. They're derived using calculus and Newton's equations only. Super useful and super interesting. That's how we determined the trajectories of the planets and the positions of the stars and things. Very cool. So good luck. Thanks for watching. I love doing this stuff, so let me know if you have any questions, and have fun.